So I'm Petros Koumoutsakos. I'm the faculty director for the Institute of Applied Computational Science. And it's my distinct pleasure to introduce today Emma Pierson. And it's distinct because Emma is working on two of the biggest challenges, perhaps, of our times. And one of them is healthcare, and the other one is inequality. And she's actually working using some of the tools that are very important and very researched and studied these days. It's data science and in particular machine learning methods. So it's very exciting to hear what Emma will tell us today. A few things about her studies. She did her PhD with Jure Leskovec at Stanford. And then before that, she did a master's in statistics at Oxford on a Rhodes Scholarship. And before that, she even spent a year as a data scientist at 23andMe and in Coursera. And beginning the summer of 2021, Emma will be an assistant professor of computer science at Cornell Tech at the Cornell University, the new New York City campus. Besides her great papers that they span Nature Medicine, Nature Human Behavior, and other great journals, she has also been finding time to write for the New York Times, 538, Times Higher Education, and she's actually curating a blog. And actually in this blog, I was able to find what are the favorite things of Emma, and I hope she would not mind that they will be announced with a Greek accent. So the favorite things of Emma are raindrops on roses and whiskers on kittens, matrix transposes and not overfitting, well-maintained packages, clear docu streams, networks with very low latency pings. And Emma, the floor is yours. I'm looking forward to your.
Can everyone hear me okay? Yes, great. Yes. Thank you for that very surprising introduction. Yes, that comes from a blog post where I adapted the Sound of Music classic to write about some of the things I like in academia. So it's a pleasure to be here. I'm actually about 20 miles from the Harvard campus right now, so I'm staying in Boston, and so I wish I could be there in person with all of you today. That fact notwithstanding, today I'm going to be talking about data science for social equality. So to motivate this talk, I think it's unnecessary to belabor the point that our society remains deeply unequal, right? You see this along virtually every demographic dimension, from race to socioeconomic status to gender, and I suspect you already know this, so I won't spend long on this point. Slightly less well-known, but probably also well-known among this audience, is the fact that computer scientists can and have exacerbated this inequality. We see this in language processing. When we try to train language algorithms on text written by humans, the algorithms learn undesirable stereotypes from the text, like man is to computer programmer, as woman is to homemaker. This is unsurprising since algorithms pick up on patterns of all kinds, but it's a big problem if you then use these algorithms to, for example, screen resumes, and they rank women's resumes as less good for computer science jobs. We see this in computer vision. This is a picture of Joy Buolamwini, an MIT researcher who realized she had to wear a white mask for an algorithm to detect her face. In subsequent work with Timnit Gebru, she's shown that algorithms are more likely to misclassify the gender of darker-skinned women. We see this in healthcare, when a widely used algorithm used to predict health risks shows racial bias. Black patients with a given risk score are sicker than white patients with the same risk score. This occurs because the algorithm was trained to predict cost as a proxy for health, and Black patients who have unequal access to care have less money spent on them than equivalently sick white patients. In general, there have been so many similar examples of this in recent years that literally multiple books have been written on it. The overall message is simple. Far from being a panacea to social inequality, computer science can actually exacerbate it. Today, though, I want to tell you about a more optimistic counterpoint, that data science and machine learning, properly applied, can also reduce inequality. Given our role in increasing it, this represents not just an opportunity, but an obligation. Specifically today, I'm going to be telling you 3 stories about how we can sort of improve healthcare for underserved populations. In the first story, I'll tell you about studying racial and socioeconomic disparities in pain. Then I'll talk about understanding women's health and women's cycles. And I'll close the talk by talking about data science methods for understanding disparities in COVID. So let's get right into it and talk about disparities in pain. This is joint work with David Cutler at Harvard, Yuri Leskovic at Stanford, Senil Mullainathan at Harvard, and then at UChicago, and Ziad Obermeyer, who was at Harvard, and then at Berkeley. A lot of people fleeing Boston here, I guess. Okay, so a general fact about pain is that disadvantaged groups experience more of it. You see this for socioeconomically disadvantaged groups. You see it across a variety of types of medical conditions, across multiple continents, across multiple sample types. It's quite a robust finding, and you see it for racially disadvantaged groups as well. And this is also true in the condition I'll be telling you about today, knee osteoarthritis, which is one of the most common causes of disabling pain in older adults. Multiple people listening to this talk will probably develop knee osteoarthritis if they haven't done so already. It's a very common cause of disabling pain. And in this condition, as in other conditions, disadvantaged groups experience greater pain. Now, a natural explanation is, well, perhaps they just have worse knee osteoarthritis. But here's the interesting part. These groups have worse pain even when you control for how severe the doctor thinks the disease is. So I want to make that statement quantitatively precise for you. But for you to understand what the numbers mean, I have to tell you what I mean by pain, how we measure pain, and how we measure severity. So let's talk about that. So how do we measure severity in knee osteoarthritis? Well, the traditional way to do it is that a doctor looks at an X-ray of the patient's knee and assesses it on various clinical features, like does the patient have osteophytes, bone spurs, is the joint space reduced, etc. And then they summarize those measures into a single number called Kellgren-Lawrence grade, which is a categorical scale, ranges from 0 to 4, with higher scores denoting worse pain. I'll call that KLG throughout the talk. But basically, doctor looks at an X-ray and rates it in terms of disease severity. How do we measure pain? Well, we ask the patient a bunch of questions like how much pain do you feel when you're bending your knee, when you're going up the stairs, etc. The results of those questions are then aggregated into a single score called Coues pain score. The data I'm going to be talking about today comes from the Osteoarthritis Initiative. This is a publicly available resource. It's very widely used. All the results you're going to see are presented on about 1,300 people. And we're going to be comparing pain by 3 binary groupings. We're going to be comparing Black to non-Black patients, and almost all the non-Black patients are white. We'll be comparing lower to higher income patients and lower to higher education patients. So what do I mean when I say disadvantaged patients have more pain? So here what I'm showing you is a vertical histogram with Black patients in orange and other patients in blue. And you can see pain is on the y-axis, lower scores are worse pain. And you can see that there's a clear visual disparity between the two histograms. And if you want to summarize that in a single number, you can take a simple difference in means. That's about 10.6 points on the Coues scale. And that's a substantial gap. It's 2/3 of the standard deviation of the whole data set. So pretty big pain gap. The gaps for income and education are smaller, but still substantial. So what happens when we control for severity, for that KLG score I told you about? Well, the results of that analysis are shown in the graph at right. So now I've plotted severity, that KLG score, on the x-axis, and I've plotted pain on the y-axis. Sorry, let me adjust this slightly so you can see. There. And I plotted pain on the y-axis. And the important point is that there's still a gap between that blue and orange line. A pain gap remains between Black patients and non-Black patients, even when we control for severity. If we want to summarize the size of that gap in a single number, the standard way to do so is with a linear regression where we regress pain on race and KLG. And then the pain gap is the race coefficient when we control for KLG. And the results of that analysis are shown in the table. You can see that that pain gap gets smaller, but not that much smaller, right? It goes from, for example, 10.6 points to 9.7 points for race, which is to say it gets about 9% smaller. Really, controlling for severity doesn't do that much to narrow the pain gap. This isn't just true in our data set, by the way. Other studies find this as well. The goal of our paper is to explain why this is. Why does a gap in pain persist, even when we control for how severe the doctor thinks the disease is? In particular, we're going to try and distinguish between 2 hypotheses. The first hypothesis is what we call the outside the knee is theory, namely that there are non-knee related factors which are causing disadvantaged patients to experience greater pain even when their knee disease is no more severe. So what's such a possibility? Things like higher life stress, less access to pain medication, various other possibilities. And all of these have been suggested by prior literature, and a common element is that all of them are outside the knees, so they're not visible in a knee X-ray. But there's a second possibility as well, right? And that's what we call the in their knees theory, namely that there are pain-related ailments in the knee x-ray which KLG isn't capturing. And if we could capture those things, we'd be able to explain more of the pain gap. So under the first hypothesis, there's nothing to be seen in the knee x-ray that would help explain this pain gap. And under the second hypothesis, there is something to be seen. So why is the second hypothesis even possible, right? Like, why is this just some crazy thing we dreamed up? Well, here are two reasons we might believe it could be true. The first is that we don't understand pain all that well. This is true in general. It's also true in knee osteoarthritis more specifically. KLG just doesn't explain all that much of the variance in pain. And a possible reason for this is that KLG was developed decades ago in heavily white British populations. And so it's plausible, right, that it's not capturing all the factors that are relevant to pain in modern and more diverse populations who live and work very differently and consequently suffer different occupational environmental factors. So we're going to try and assess whether there are overlooked physical features in the knee which would explain the higher pain levels in disadvantaged groups. This isn't just an academically interesting question. It's a question with concrete clinical implications. And the reason is that whether you get knee surgery depends on whether the source of your pain is in your knee. If you go to the doctor in a lot of pain and she looks at your knee and she says, "I'm sorry, I can't see anything wrong with this," then she's quite unlikely to prescribe you surgery for an apparently healthy knee. It's more likely that she'll prescribe you things, non-specific therapies, like opioids, for example. On the other hand, if you go to the doctor in a lot of pain and she looks at your knee and she says, "Aha, I know exactly what's wrong with this, very high grade on the Kellgren-Lawrence scale," then it's more likely under clinical guidelines that she's going to prescribe you surgery. Consequently, if clinical severity scores are missing true sources of pain within the knee in disadvantaged groups, those groups may be under-referred for surgery. Okay, so that's the basic question. How are we going to answer it? How are we going to look for this additional signal in the knee x-ray? Well, of course, this being, a medical image, we're going to do the only thing which makes sense these days, which is to train an algorithm, a convolutional neural network, to search for this additional signal in the knee x-ray, which could potentially help explain the higher pain levels in disadvantaged groups. How are we actually going to set up that prediction task? Well, the standard way to using deep learning to extract signal from a medical image is to train the model to replicate the doctor's judgment, right? Which here means train the model to predict KLG. And this is such a standard setup that, in fact, multiple papers have been written on exactly this task. But there's a problem with this, right? If KLG doesn't capture all the pain-relevant features, we don't just want to train the model to replicate it. Our whole hypothesis is that that clinical risk score might be biased or incomplete. So we don't want to train the algorithm just to recapitulate knowledge, which is potentially biased or incomplete. Rather, we're going to train the model to learn from the patient directly by predicting the KOOS pain score, that self-reported patient pain, directly from the knee. So to be very concrete, the input to the model is an x-ray of the knee. The output is a knee-specific pain prediction, which we term ALGP for algorithmic severity measure. And if we find that controlling for the algorithmic severity measure, ALGP, narrows the pain gap more than controlling for the clinician severity measure, KLG, it implies that the clinician severity score overlooks knee features which would help explain disadvantaged patients' higher pain levels. Before I go to the results, any burning questions about what we're even doing? Great. Okay, so first result is that the algorithm does in fact find additional signal for pain in the knee x-ray. We find that ALGP, the algorithm severity score, predicts pain better than does the clinician severity score, KLG. It achieves a higher R-squared with a statistically significant difference, and you see similar results for other predictive measures. But of course, those R-squareds really aren't all that high, right? And that isn't the central question of the analysis anyway. The central question is, when we control for the algorithmic severity score, does it narrow that pain gap? And it turns out that the answer to that second question is also yes. So here, that first column is just what I showed you before. It's how much smaller does the pain gap get when we control for the clinician severity score. But the middle numerical column is new. It's how much smaller does the pain gap get when we control for the algorithm severity score instead. And the final column gives the ratio of the first two columns. So you can see, for example, for the race pain gap, the clinician severity score explains only 9%, but the algorithm explains 43%, and the ratio of those two numbers is 4.7. Results for income and education are qualitatively similar, although a little less dramatic. The overall implication is that there is overlooked signal in the knee X-ray, which would help explain disadvantaged patients' higher pain levels. So you can tell I'm cool here because I did a meme. I'm very proud of myself here. So a general principle. Thank you. When fitting neural nets in medicine and neural nets in general, right, is that you should be very nervous about them picking up potential confounds and other signal that you don't want them to pick up on, because neural nets are sort of like these super powered learning algorithms that will latch onto signal in anything. So I'm not going to talk about these robustness checks in great detail, although if you have specific questions or things you're worried about, I'm happy to talk about them. But here are a number of the things we checked for that you might be worried about, that we assessed and did not think that the algorithm was doing on the basis of the evidence we saw. Okay. Two other accessory results I briefly want to talk about. The first is that data set diversity contributes to model performance. So there's been a lot of concern in medicine, right, that like we've been doing our studies on historically like non-diverse populations. So we've been doing things like, let's throw all the women out of our studies, or like, let's train our models only on like people of white European ancestry and things like this. And there's been concern that like that might limit the generalizability of our findings and mean that we aren't understanding everything we need to understand about populations. So we seek to assess the effects of data set diversity. We try training the model under two conditions. First, on a non-diverse train set from which we've removed all the Black patients. And second, on a diverse train set from which we've removed the same number of non-Black patients. So in both cases, the size of the training set remains constant. The only thing we're changing is the racial diversity of the data set. And what we find is that while both models outperform KLG, using a diverse train set further boosts our performance. So we get better predicted performance for pain, we get a bigger reduction in the pain gap. You see similar results for income and education as well. The overall implication here is that data set diversity is an important contributor to model performance. Finally, to discuss briefly the clinical implications of these results. So as I said, one of the reasons we care about these severity scores is that they influence the allocation of surgery. So to see how allocation of surgery might change if we use the algorithm severity score as opposed to the clinician severity score, we replicate a previous clinical guideline where we say, look, we're going to give knee surgery to patients who have both high pain and severe disease. But we try measuring severity in two different ways, using KLG or using ALG-P. And what we find is that because the algorithm severity score ALG-P tends to give disadvantaged patients higher severity scores, it also is more likely to refer them for surgery. For example, among Black patients, people are roughly twice as likely to be eligible for surgery when using the algorithm severity score as opposed to KLG. So this is sort of one of the concrete clinical implications. Use of algorithmic scores could potentially sort of reduce disparities in access to surgery. Okay, so to summarize this story, we trained a deep learning model to predict pain from knee X-rays. We showed that it found overlooked signal, which would help explain disadvantaged patients' higher pain. And a concrete clinical implication is that disadvantaged groups may be under-referred for surgery. Just to put this within sort of the broader literature in algorithmic fairness and how can we make algorithms more fair. As I said, there's been a lot of previous work on how algorithms and machine learning methods can increase disparities in medicine and other domains. This is sort of the more optimistic flip side about how we can also reduce disparities by detecting signal that humans miss. Key to our results here were, first, we chose a prediction task where we didn't just replicate clinical knowledge, but we sought to learn from the patient. So we didn't just recapitulate sort of potentially incomplete or biased medical knowledge. And secondly, we trained the model on a diverse data set. And I should say, by the way, that this was only possible because of the OAI data set to begin with was collected in a way that was deliberately racially diverse. And that was very important to our ability to do this analysis. All right, second story. This is about women's cycles. This is joint work with Tim Althoff, who is now a professor at UW, Daniel Thomas, who's our industry collaborator at the company that provided the data, as I'll say, Paula Hillard, who is a gynecologist at Stanford, and Yuri Leskovic, my advisor, who's a computer scientist at Stanford. And you can find the paper online in Nature Human Behavior, although it might be paywalled. So if you want to read it, just like bother me and I'll send it to you. Cool. Okay, so cycles are very important to human health, right? You know, you've got daily cycles like circadian rhythms. You've got weekly cycles like I'm going to sleep in tomorrow, hopefully. You know, you've got seasonal cycles like people get depressed in the winter. And then, of course, you've also got the menstrual cycle. And the menstrual cycle itself is very important. It's implicated in everything from cancer to schizophrenia to pregnancy. It's really a wide range of medical conditions. Unfortunately, stigma and lack of large-scale data have hampered study of the menstrual cycle. And you see this in a whole bunch of different ways, different modalities. So for example, you see it in medical data sets where information on the cycle is often lacking from medical records and from global health data. You see it in health tracking apps like Apple and Fitbit, which were slow to add cycle information until there was popular outcry. You see it in the clinic when clinicians don't always consider this fundamental aspect of women's health. And you see it in the broader culture as well, which stigmatizes discussion of the menstrual cycle. And like, this is not some abstract, feminist studies academic thing. Like, this results in concrete harm to the health of half the global population. This is a big deal. Just to give you two example stories of this, the girl on the left is required to stay in that tiny hut outside when she's on her period as a consequence of stigma associated with the cycle in Nepal, where she lives. And it's like not hard to see why this could be potentially dangerous, right? Women forced to do this have been bitten by snakes, they've been sexually assaulted, they've died of smoke inhalation. So it's like, a practice that concretely harms the health of young women. The woman on the right is Noemi El-Haddad, who's a professor of biomedical data science at Columbia, who has suffered for much of her adult life with pain from endometriosis. This is a condition linked with the menstrual cycle, which is still very poorly understood. So this is sort of how stigma and lack of information about the cycle harms women's health. So that's a little depressing, but there is good news here, which is that women's health apps offer new potential for understanding and destigmatizing this aspect of women's health. Specifically, today we're going to be talking about the Clue Women's Health app. So this is an app used by millions of women across more than 100 countries, and it tracks more than 100 features daily, including mood, pain, sexual activity, and crucially, for our purposes, when the menstrual cycle starts. So to give you an example of the data that people can log with this app, and I should say this is purely simulated for patient privacy reasons, but it gives you sort of a sense of what people can log. People can log when their periods start. So here, the vertical axis is showing sort of various features that people can log with this app, and the x-axis is showing the day, so sort of over time, and the vertical black lines are showing sort of the inferred date of menstrual cycle starts based on when period starts. And that, they can log continuous features like resting heart rate or like weight. And they can also log other categorical features of mood and behavior, like sexual feelings and behavior, like social feelings, mental state, etc. So in this paper, what we do is we provide the first decomposition of women's mood, behavior, and vital signs into 4 simultaneous cycles. Those 4 cycles I told you about before, the daily, weekly, seasonal, and menstrual cycles. And by doing so, we're going to improve understanding of this fundamental aspect of women's health. So our data set consists of millions of women, hundreds of millions of observations from more than 100 countries, and we're going to be studying cycles in 15 dimensions of mood, behavior, and vital signs. So for example, happy, sad mood, or resting heart rate. So let's just take a look at how previous studies tend to study cycles. Very common thing they do is they just take a population average at each time point. So this is from a study published in Science about 10 years ago. They used Twitter data to sort of plot how happiness, that's on the vertical axis, changes over the course of the day and over the week. And so what they're doing here is like the value for like 3 p.m. on a Thursday is just the whole population average at 3 p.m. on a Thursday. And you can see that like this reveals various things, right? That like people tend to be happier on the weekends, for example, and that happiness fluctuates over the course of the day. This is another study, also on Twitter data, looking at a longer time period. So you can see here the x-axis is sort of over years, and you can see sort of weekly variability. You can see sort of long seasonal time trends. You can see holiday effects. So it's clear that this previous methodology is pretty useful. And we can do this on our data as well. So here I'm making the exact same plot on our data. You're plotting this sort of happy, sad mood over time. And you can see, for example, weekly cycles, that's that high frequency oscillation in the plot. You can also see outliers like Christmas, the green dot, and the day after the 2016 election, purple dot, which is like this enormous outlier in the negative direction, sort of unsurprising given that it's a predominantly young and female population across, an international community. But there's a problem with this view, right? Which is that averaging in this way is going to make the menstrual cycle invisible. Why is this? Because people are at different points in their menstrual cycle on January 3rd, for example. So if you take a population average on January 3rd, you're going to average across all these phases. The phases are not in sync, and that source of variation is going to disappear. And it turns out that this is pretty important Now that red line is plotting a counterfactual where we could actually observe that menstrual cycle variation, and you can see that it would considerably contribute to cyclic variability. So now let me tell you how we get that red line. Just to sort of put this in quantitative terms, you can see that the menstrual cycle amplitude is fairly substantial relative to outlier events, like, for example, Christmas. Okay, so methodologically, how do we actually get that? How do we decompose into 4 cycles? We're going to use multiple regression, so OLS, ordinary least squares, to decompose into 4 simultaneous cycles. We're going to take each observation, and what is an observation here? For happiness, it would be mood for one person at one time point. So that's the dependent variable. The independent variables, the right-hand side of the regression that we're going to regress upon, are categorical variables which capture the 4 cycles. We're going to have a categorical variable for hour of day, like 3 p.m., for day of week, like Sunday, Monday, Tuesday, for month of year, like December, and then for day of menstrual cycle, for example, 3 days after period start. And then we're going to plot those regression coefficients, and they're going to capture the cycles. So this shows you the example for happy, sad, mood. So here, the vertical axis is plotting the regression coefficients, and each plot is showing the regression coefficients for one cycle. From left, the menstrual, daily, weekly, and seasonal cycles. And so you can see sort of lots of effects here, right? You can see a decrease in happy, sad, mood right prior to period start. You can see this sort of daily fluctuation. You can see the weekly fluctuation with sort of people getting happier on the weekends and sort of a seasonal dip in mood about the time that school starts, this being, sort of often in school population. But another important thing here is that you can see that the menstrual cycle amplitude is substantial relative to the amplitude of the other 3 cycles. It's in fact the largest cycle for this particular dimension of mood and behavior. So the overall implication, this is why menstrual data is quite important. Without it, the largest cycle for this dimension of happy, sad mood is in fact invisible. This isn't just true for happy, sad mood. We examined 14 other dimensions of mood, behavior, and vital signs. And here, the vertical axis is plotting the amplitude of each of those 4 cycles. So sort of the maximum regression coefficient minus the minimum regression coefficient. And you can see that for 11 of the 15 cycles, the menstrual cycle, in fact, has the largest amplitude. We do a number of robustness checks on both the model and the data, and this result is quite robust. Another thing our large data set enables to examine is how does this vary across cultures? And so basically we examine the data set for each country independently, and we find sort of directionality, which is consistent in menstrual effects. So consistently people get less happy prior to their period start. This is sort of interest because it's been previously sort of uncertain, because a lot of studies of the menstrual cycle were done on the 44 women from a liberal arts college in Connecticut or something, right? And it's kind of unclear how much their conclusions generalize. Okay, so I want to be very clear about what these results do not imply. We are not saying that women are more volatile here. So first, our analysis, of course, makes no comparison across genders or sexes. That's not a comparison we do at all in our analysis. And indeed, previous research does not find sex differences in volatility. There's this great paper entitled "Female Rats Are Not More Variable Than Male Rats" by an author who is clearly quite fed up with this whole trope. Why does it not find sex differences in volatility? Well, here are 2 obvious reasons. The first is that there are male hormone cycles as well. There's just been less cultural attention paid to them. And I think that would be a fascinating thing to study if we had data on them. I think a second thing is that cycles aren't the only source of volatility, right? We're just comparing the amplitude of 4 cycles, but we're not looking at all at variability induced due to things like, I don't know, your football team losing a big game or something like that. So our analysis simply implies that the menstrual cycle is an important cycle relative to the other 3 cycles. It does not imply that it explains all or even a substantial fraction of variation within people or between people. Okay. So to summarize, stigma, lack of large-scale data have hampered study of this fundamental cycle. And this is really bad because it's a primary contributor to cyclic human variation, as our new analysis shows. The good news is that new women's health data sets offer unique potential for understanding the menstrual cycle, but also women's health more broadly. And I'd be happy to talk about potential directions there. I should mention this is only one of 3 papers we actually wrote on the menstrual cycle. We also wrote one on pregnancy. We also wrote a pure methods paper on this data set. So I think it's a really rich data source for understanding people's lives. And I'm happy to chat more about that. Cool. Any questions before I go on to the final part of the talk? Great. Okay, so the final story I want to tell you today is about disparities in COVID. Okay. Yeah, the final story I want to tell you today is about disparities in COVID. And this is joint work led by Serena Chang, who's a computer science PhD student at Stanford, Pangwei Ko, who's also a computer science PhD student at Stanford, and then with Jolene Gerardine, who's an epidemiologist at Northwestern, Beth Redbird, who's a sociologist at Northwestern, David Grusky, who's a sociologist at Stanford, and then Yuri Leskovic, who's a computer scientist at Stanford. So it's like an extremely interdisciplinary team, which I think is very useful for doing COVID work. Cool. Okay. So as you all know, viruses like COVID spread through human contact, right? That's why we're doing this talk remotely rather than in person, which is to say that there is an underlying contact network that modulates the spread of the virus. Oh, I should just say before I start, this paper is, I think, freely available online. You can find it. It was published in Nature a couple months ago, but I think it's not paywalled, so you should be able to find it. Okay. So there's sort of some underlying contact network connecting person to person that modulates the spread of the virus. So a simple epidemiological model is that an infected person can infect anyone she comes into contact with some probability. Those people can then infect their contacts, and then you get the sort of spread of the virus across the network. Now, as a consequence, understanding and sort of measuring this contact network is incredibly important, right, for understanding the spread of the virus. But of course, it's quite hard to know exactly what this contact network is, right? It's very hard to know who everyone comes into contact with. Consequently, current models use simplistic methods to sort of estimate the underlying contact networks. They make necessary simplifying assumptions. For example, you might assume that anyone can infect anyone, so the network is fully connected. Or you might use a network that captures trends at a very high level, like an airline network connecting city to city, but doesn't tell you anything about movement within a city. Or you might use historical data. You might say, look, I know what people were doing in 2015. Hopefully they're still moving the same way now in 2020 or 2021. But it's easy to see, right, why this might not be enough for accurately modeling the spread of COVID in the present day. The first reason is that we're undergoing this incredibly dramatic change in human mobility. Like, oh my gosh, like, let's hope we never have to do this again, right? We've got, reopening policies, stay-at-home orders, yeah. And the second reason is that the kinds of questions we're interested in answering often depend in a very fine-grained way on human mobility. So we might want to understand the effects of very specific reopening policies. What happens if we reopen restaurants, but only from 6 to 9 p.m. and only to 75% capacity? We also might want to understand things like inequality in infections due to differences in mobility patterns, like why are some socioeconomic groups getting infected at higher rates? And it's clear that like using data that doesn't capture sort of these fine-grained trends, like assuming that everyone is connected to everyone equally, or like using an airline network, is not going to tell you anything about like socioeconomic disparities in infection rates within Boston. So in our paper, what we do is we first estimate that human mobility network in a fine-grained way using cell phone data. And then we put an epidemiological model on top of the network in order to capture transmission. I could keep going, but I'm seeing that people are asking questions. Are any of these clarifying questions that I should answer now because people are confused? It's fine if not. I'm also happy to keep going.
Keep going. Yeah. We might ask questions at the end, I think.
No, that sounds good. I trust you. Great. Okay, so we're going to try and estimate this network. So I want to be concrete about the network we're trying to estimate. Our network is going to capture visits of people to places. So people here are census block groups, basically they're neighborhoods. So we're not actually capturing the movement of individual people. We're talking about visits from neighborhoods of which are areas which about 600 to 3,000 people live. So they're relatively fine-grained neighborhoods. And then we're talking about visits from those neighborhoods to places. I'll call places POIs throughout this talk, points of interest. And those are non-home locations that people go when they're not at home, like restaurants, cafes, grocery stores, etc. So the network we're estimating is going to be connecting these neighborhoods to places. And the network is going to change hour by hour. So at every hour, we want to infer how many people from a given neighborhood, a given CBG, visited a given POI. So you can think of this as sort of a list of networks, one network for each hour, or you can think of it as a giant 3D tensor cube thing. But that's the object of interest we're going to try and estimate. Now, how are we actually going to estimate this? Well, we're going to use data from a company called SafeGraph, which has made its data freely available to people researching COVID. SafeGraph is a company that takes anonymized aggregated location data from numerous cell phone apps. So, there are cell phone apps that will track people's location with consent from the user, and then some of those apps will then sell their data to SafeGraph. So SafeGraph is an aggregator of that information. All the data we're going to be using is totally anonymized and it's aggregated. So we don't know anything about the motion of individual people, and we certainly don't know who anyone is. Our data set that we're going to be analyzing is going to be in 10 of the largest metropolitan statistical areas in the United States, so places like Chicago or New York. In total, we're going to be capturing the movements of about 98 million people. Importantly, we're going to be studying we're going to be studying infections in each metropolitan statistical area, each MSA separately. So we're not going to be studying stuff like travel between New York and LA. And a final thing to be aware of is that we're going to be studying analysis from the first wave of infections in spring of 2020, March to May 2020. The reason is that's the data that was available when we wrote the paper. And I'll talk a little bit about how we're updating it on new data now. So what data do we actually get from SafeGraph on these 10 cities? So SafeGraph tells us first, at a very fine-grained time scale, so sort of on an hourly time scale, how many people leave each neighborhood and how many people go to each POI. It also tells us on a monthly timescale, so much less fine-grained, the total number of visits from each CBG to each POI. And finally, it gives us some basic metadata about each POI, each restaurant, each grocery store, like how big is it in square feet? How long do people tend to stay there? And what category of business is it? So we want to combine these ingredients in order to estimate the actual hourly network connecting neighborhoods to POIs. So what's the basic problem here, right? We know at an hourly level, the number of people going out and the number of people coming into each POI, but we don't actually have the network linking those two things at an hourly level. All we have is an aggregated monthly view of that network. So you can think of it basically as you can think of this basically as a matrix where we know the row sums of the matrix, the column sums of the matrix, and we have a noisy estimate of the matrix itself. Fortunately, there's an algorithm designed exactly for this purpose called iterative proportional fitting. Iterative proportional fitting says if you have these three ingredients, you have the row sums, the column sums, and a noisy estimate of the matrix, then I will give you as output a matrix which is consistent with those row and column sums and subject to that constraint as similar as possible to the initial noisy matrix. So that's what we do. At each hour, we take the IPF algorithm, we apply it to the original SafeGraph data in order to infer an estimate of the hourly network linking CBGs, neighborhoods, to POIs, places like restaurants. In total, our networks encompass about 500,000 POIs, tens of thousands of CBGs, neighborhoods, and about billions of hourly edges. So that got a little mathy and abstract. I want to just give you a concrete example of what we ended up getting as output here. So this is for the Chicago metro area, and I'm showing you time slices of the network at 2 different hours. The first is from early March, prior to social distancing, when we were all kind of going about our lives as normal, and then the second time slice is after social distancing sort of took place in early April. And so each gray line here is linking, basically telling you the number of hourly visits from a given CBG to a given POI. So you can see a couple things from this view, right? You can see that the density of the gray lines gets lower from March till April, indicating that mobility decreases after social distancing takes effect. You can also see that most of the gray lines are vertical, indicating that people mostly hang around their own homes. We've made our networks publicly available, by the way, if you want to reproduce our work or build on it. Okay, so that's our network. So now we have to put a model on top of it, right? So the model we put on this network is called an SEIR model, which is a term which has probably gone up like exponentially in the news over the past few months, right? So crash course on SEIR models, very standard epidemiological model. And basically what an SEIR model says is it imagines people move through 4 states, SEIR, in that order. You can't go in any other order. So what are these 4 states? When a disease has not entered a population, people start in the S state, the susceptible state, meaning they haven't caught the disease, but they can catch it. Now, if they come into contact with someone who's infectious, then they run the risk of going into the exposed state, which is to say they have the disease themselves, but they're not yet infectious to other people. After some period of time, they move from the E state to the I state, which is to say they're now infectious, they're dangerous to other people. And then after some further period of time, they move into the removed state, which is to say, perhaps they've recovered, perhaps they've died, but at any rate, they are no longer able to give the disease to other people. So what we do in our model is that for each neighborhood, at each hour, we remember the fraction of people in each of these 4 states. So we might say in neighborhood 7, at hour 4, 93% of people are in the S state, 6% of people are in the E state, 0.7% of people are in the I state, and 0.3% of people are in the R state, right? And so you maintain that hour by hour. Now I'm going to tell you how we actually specify how people transition through those 4 states. Okay, so we need to write down the rules specifying how people transition through these 4 states. It turns out that the last 2 transitions in our model, from E to I and from I to R, are pretty simple and boring. Basically, at each time step, you have some probability of transitioning to the next state. We take that probability from the prior literature. But that first transition, from S to E, that's sort of the crucial secret sauce in the model. Intuitively, that's the transition that really depends upon mobility, because whether you get exposed to the disease depends on whom you come into contact with. Our model assumes that new infections, so these S to E transitions, can occur in 2 ways, at CBGs and at POIs. So those CBG infections are capturing stuff like you yourself were home, but unfortunately someone in your home was sick and now you yourself are sick. POI infections are like you went out to a bar, unfortunately someone at the bar was sick, and now you yourself are sick. So the model assumes that the probability of getting infected through that first pathway, the CBG infection rate, is just proportional to the fraction of the CBG which is infected. In other words, neighborhoods are more dangerous if a higher fraction of the neighborhood is infected. The second pathway, the POI infection rate, is only slightly more complicated. It assumes that the probability that you get infected at a POI is proportional to the fraction of the POI that is infected times a POI-specific factor, which captures things like how big is the POI and how long do people stay there. Intuitively, POIs are more dangerous if they're smaller and if people stay there longer. Now, how do we actually fit this model? A nice thing about this model is that it only has 3 free parameters for each city, which stay fixed over time. Those parameters scale those 2 infection pathways, so sort of the rate of getting infected at CBGs, the rate of getting infected at POIs, and then the final parameter just specifies the initial conditions to the model. It says how many people in the city were infected on March 1. In terms of choosing the best fit model, we do grid search over all the parameter combinations, and we choose the parameter settings which achieve the best fit to the reported daily cases. We can talk about this more in the question period if it's of interest, but basically we choose the parameters that yield a good fit to observed real-world data. Okay, so just to make things a little more concrete, this is sort of what the actual model output looks like. I'm glad the movie is actually playing. So the graph at left is showing just raw data input to the model. It's the number of visits to POIs over time. And so the simulation starts at March 1, and you can see sort of this dramatic fall in mobility about 2 or 3 weeks into the simulation. That's when social distancing is taking effect. The middle graph, and this is in Chicago, by the way. The middle graph is showing you actual model output. It's showing you what fraction of the population the model thinks is in each of those states over time. And you can see sort of that the number of people in the E, I, and R states is rising over time on the log scale on the y-axis. And the final graph on the right is showing you sort of a map of the Chicago MSA. And it's showing you where the model thinks people are actually getting infected. You should take this with a grain of salt because we only fit the model to the MSA level case count. So we can't actually validate that those very fine-grained predictions are accurate. But it is still interesting to observe that the model is predicting that people are getting infected at higher rates in that dense city center. And we'll return to that point in a little bit. Now, of course, anyone can make pretty pictures. Do these actually correspond to reality at all? It turns out that they do correspond pretty well. So the big graph at left, I'm showing you Chicago because that's what I'm using as a running example throughout, although you can find the results for the other 9 MSAs in the paper. So you can see here the orange line is the actual reported cases, and the blue line is the model predictions with confidence intervals shaded, and then the x-axis is time. And you can see that actually we do achieve a pretty good fit to the daily confirmed cases. And then you can see the fit for the other 9 cities, and the fit is similarly pretty good. You might ask, like, oh, could you do as well with a baseline model? We do check that out, and we find that using the mobility data actually does improve the fit a bit. Okay, so what can we actually do with this fancy model that we've built out? Well, you can use it to answer a number of policy questions of interest. So you can ask it, what is the impact of various social distancing measures? You can ask it to forecast the effects of various reopening strategies, like what happens if we reopen restaurants to a given degree? What's the impact on predicted infections? But the question I want to focus on today, although you can find the answers to those other questions in the paper, is how does this model help you explain socioeconomic and racial disparities in COVID cases? So we know, right, not from our work, from the previous literature, that socially disadvantaged groups, lower income groups, racially disadvantaged groups were hit harder by COVID-19. So this was true for many reasons, but some of them have to do with mobility, plausibly, right? For example, if you're more likely to be an essential worker, you have to go out more, you face higher risk of infection. So we want to know first, does our model naturally learn to predict these observed real-world disparities in case rates? And secondly, if it does it help us explain why it is? Now, importantly, we don't actually observe the movements of individual people. So what we have to do is we have to compare lower income to higher income neighborhoods. So for example, we might say within a city, let's compare people in the bottom income decile of neighborhoods to the top income decile of neighborhoods and compare predicted infection rates in those two groups of neighborhoods. So a first main result from the model is that it does in fact predict these real-world disparities. Here, the left graph is showing you how much likelier are lower income neighborhoods to get infected. And the right graph is showing you how much likelier are less white neighborhoods to get infected. And you see that in both cases, the values are to the right of 1, indicating higher risks for disadvantaged groups. So the model is correctly predicting socioeconomic and racial disparities on the basis of mobility patterns alone. The model is also able to explain or provide 2 mechanisms related to mobility explaining why these disparities emerge. The first reason you probably already guessed, because I hinted at it, it's that people from these neighborhoods were less able to reduce their mobility. This is plausibly linked to the fact that there are occupational differences where they were more likely to have to work in high-risk jobs that required them to leave their homes. A second reason is a little subtler, though, and it's that the POIs visited by people from these neighborhoods were smaller and more crowded and therefore more dangerous. For example, if someone from a lower income neighborhood and someone from a higher income neighborhood both went to the grocery store, the person from the lower income neighborhood would tend to go to a grocery store that was smaller and more crowded and therefore more dangerous, even in the course of living their normal life in the exact same way. This is very consistent with what we know about differences in population density and how they correlate with income. So to sort of show you a movie from Philadelphia, a city where we predict the emergence of large disparities, focus on the graph in the middle, you can see that the model is predicting higher infection rates, sort of that red stain, at the very center of the city. And in fact, that red stain is exactly the region, if you look at the 2 graphs at right, with the highest population density and the lowest income. So that's sort of the connection between, income and density and infection rates. The reason I'm focusing on income, by the way, is because that was sort of the disparity that showed the largest effect in our data. But there are similar results for racial disparities as well, and you can find those results in the paper. A corollary to all this is that it's very important that reopening plans don't just consider the impact on the population as a whole, but specifically consider the disparate impact on lower income groups, for example. And to their credit, policymakers are now really taking this effect into account. Like, it's clear that it's a primary focus of the Biden administration, for example, and that's as it should be. So just to close, there are some important caveats to keep in mind here. Our analysis is from spring 2020. Our data doesn't cover all POIs and all people. So for example, prisoners are an important vulnerable population who are probably not well covered in our data. Our model itself is parsimonious. We don't try and model things like mask wearing, asymptomatic transmission, or age-related variation. But in more recent and unpublished work, which has been led by Serena Chang, we find that the high-level conclusions still persist with a more sophisticated model on more recent data. So in terms of takeaways, we presented a model that accurately fits COVID cases in the largest metropolitan area An advantage of the model is it's both scalable, even to large networks of this size, but also fine-grained, able to capture sort of heterogeneous risks across different socioeconomic or racial groups, and able to model detailed reopening strategies. And overall, this sort of analysis can help inform more efficient and equitable, importantly, reopening strategies. Thanks very much for your attention today. I've told you 3 stories, not just about how data science and AI can increase inequality, but also about how they can reduce it by shedding new light on the health of historically underserved populations. Very happy to take any questions.
Thank you very much, Emma. This was truly a tour de force. I found it fascinating, the topics that you are working with. And also it's fantastic, as you said, that AI and data science can help solve problems that instead of making them bigger. The floor is open to questions. There is a comment from Austin Crampton here that maybe you can see as well about the possible collaboration.
I can't see anything. I can't see it. I can't see the question, so by all means.
Oh, okay. So there is a really cool presentation this week by Katrina Armstrong from MGH about doing clinical epidemiology, doing this sort of work to get it to bedside for patients to triage and respond to COVID. If you hadn't had a chance to work with them, this could be a really cool point of collaboration.
I have it. I'd be very curious. Did you drop the link somewhere? I'd be curious to see it.
I can do that.
Thank you.
Yeah. Awesome stuff.
Mm-hmm.
Cecilia has a question.
Yes, I had 2 questions. Great presentation, by the way. I really enjoyed the presentation as much as the work you're presenting. So I had a question about the women's cycle study. Did you consider any other kind of diversity within your data other than geographically that you showed at the end?
Yes, we in a supplementary analysis, we look at robustness across different subsets of the population. That's like supplementary figure, like I don't know. There are too many supplementary figures. I'm sorry, but so we do assess the robustness of our conclusions across different subsets of the population. But I think an important caveat here is that there's sort of important things that I would like to be able to examine, for example, like individual socioeconomic status, which we do not have data on.
You don't have the data. Okay. I also assume that the app is not widely used for over the world and different. I don't know why you get that from an app, right?
Yeah, I mean the app is really sort of astonishingly widely used, but I think it's plausible that it's a biased population in terms of socioeconomic status and level of interest in women's health. And I think that's probably the most important caveat in the study. But I still think, every study of women's health is biased in some way. And I think this is sort of an important sort of orthogonal data source. So my thought was sort of we put this information out there, be clear about the caveats, do the robustness checks we can, and it represents an additional contribution to what's known here.
Yeah, cool. And I had another quick question. You said on the last part of your talk about the mobility, how taking into account this mobility model improves the baseline model. Can you talk a little bit about how much that affects it? Like if the improvement is, how important that is? Yeah,
so I think, where is this? I do actually have an additional slide. The 2 baselines we compare to is one we compare to one baseline where you don't use mobility data at all. We also compare to a baseline where you only use aggregate measures of mobility. So you sort of use a single aggregate measure rather than this fine-grained network. I don't offhand remember the quantitative improvements, but I do. They were significant. But I think the high level takeaway, at least for me, is not that we have a super duper predictive model, but that we have a model which it does fit real world data relatively well, but it also enables you to ask these very fine grained questions in an interpretable way. Yeah.
Okay. Thank you.
Other questions? Maybe I can ask a question on the same topic. I mean, one of the things with COVID-19 is also all these interventions. There's non-pharmaceutical interventions that governments are doing. I don't know whether you had an interest or you had a look on how this may affect inequality and how this may affect different parts of the population.
Yeah, so I'm familiar with some of this work on NPIs, and I think a general approach to this is often like you do some kind of regression, basically, where you have some measure of cases and you look at sort of the impact of various NPIs for non-pharmaceutical interventions on case rates. And I think we come at the problem from a slightly different angle, right? We don't actually explicitly look at any of these non-pharmaceutical interventions. Rather, we say, given our modeling assumptions, if you change mobility in a certain way, here's sort of the forecast model output. And that's how we get at sort of our counterfactual effect estimates, which is sort of a complementary approach to a lot of the literature, which is using sort of regression techniques where their data set is, here are the non-pharmaceutical interventions, here are the case counts, here is our predicted causal effect. We sort of pursue a different approach to that, to a related question.
Okay, other questions? People are asking whether there is a recording. I think it's posted in the Institute of Applied Computational Science website. It will be posted. Are there other questions for Emma?
Yes, I have a question.
Yeah, go ahead, please.
I'm fairly new to getting an understanding of data science and data analytics. Can you break down the difference between the two subject areas? What's the difference between data science and data analytics?
No, I don't think I can. I feel like I'm on very sticky territory, basically, whenever I try and differentiate between like machine learning, AI, data science, data analytics. I think for my own part, I often use the terms quite interchangeably. People have certainly made jokes about how, like, you say AI when you want to get like funding, and you say like statistics when you want to actually be rigorous. I would welcome other people's distinctions between data science and data analytics. I in general use these terms quite interchangeably.
Thank you.
I'm sorry, I realized that was a totally unhelpful answer. I'm sure there are folks who have better answers to this question.
I think that's a very honest answer. Thank you, Emma.
Well, another question, anybody? If not, I will ask again. I think they saw a hand. There's Austin. Yes, please.
Hey, sorry, I should have mentioned this before. I was wondering, were you looking at any of the fertility data in reference to artificial reproductive therapy, ART? I know that there's like a big push from CDC right now to try to make databases and get a better understanding of which treatment pathways are good for which populations and all that sort of stuff. So it seemed like something also that would be like a good opportunity to take a look at. Yeah, is that of interest in that area? Like, because that would be like the next step, no?
No, I mean, I think understanding the uses of data like this with respect to fertility treatments, diagnosing infertility, predicting who will become pregnant, I think that's stuff. It's clear it's a matter of pressing concern to a very large segment of the population, and like as such is of interest to me. So yes, it's definitely an interesting direction. It's obviously not what we examined in that particular study. Right. In our pregnancy paper, we kind of like make a first pass at it, but I think it's a very first pass.
Okay.
Yep.
Cool. I'll take a look. Thank you.
Perhaps the last question. Maybe I can ask one again. So there's two things that are close to my heart or to me from your talk. I also worked in these COVID models, and I also have problems with my knees. So I will ask you a question about my knee. Now, I found very interesting that you said that the algorithms, they become better when they get different types of data. And I was wondering if you had any comparison as to what happens when humans, like medical people, what is their performance compared to the performance of algorithms when the heterogeneity of the data is increasing?
No, that's super interesting. I don't know of a quantitative study of sort of how performance of human radiologists performs when or improves when given a diverse data set. And I think that's a very interesting question. I mean, it'd be great if you could do like an RCT on medical students. I hope my sister is a medical student, and I hope she's not actually attending this talk where I'm proposing RCTs on medical students. But yeah, it's a very interesting question.
Okay, I think this was fascinating. Thank you very, very much. It was very inspiring, and good luck with your post in Cornell in New York and come and talk to us again.
I hope to see you all soon. Okay, thank you very much for the invitation. I appreciate it. Bye-bye.
Thank
Very
you.
much. Thank you very much.